month. Um, so before we get started, the preamble. Please note that all our meetings are recorded and made available to the public for viewing on the YouTube channel. By participating in the meeting, it is understood that you have accepted these terms. So tonight on the agenda, um, Kevin was going to have a cool chip session, but he can't join until 8 o'clock, so we'll delay that till he arrives. Um, and then Charlie's going to talk about op amp biasing, uh, AC noise, and how we measure perspective. And then Eric's going to give us an update on FDIM North. So if you're ready to go, Charlie.
Sure, I can
Thank
do
you, sir.
that. I just need to sort out sharing again. Let's see. There's my open screen sharing. I'm going to do the entire screen, and we'll do this one. And then I will start the slideshow. All right.
Before you get started, Charlie, I have a question. Did you do a DC bias version of this before?
Yes, back in January, um, we talked about DC biasing. I'm going to take a couple of charts from that because there are a couple of folks who weren't at that presentation, and then there are a couple of folks who, me included, who've forgotten what I talked about back then. So we'll just brush over that a little bit at the beginning of this presentation.
Yeah, because I wasn't around for that meeting.
Yeah, yeah. So it'll be kind of the Coles Notes version, but it will at least give you a bit of a view of what we were talking about back then. I've kind of titled this "Everything is Relative" because when it comes to making measurements, your reference point is absolutely critical. If you haven't sorted out what that should be and what it looks like, your measurements can be pretty meaningless. And I guess it was Einstein who said everything is relative, and not to be confused with Charles Darwin's "everyone's a relative." This is so let's talk about DC biasing first of all, on just to kind of refresh everyone's memory on it.
Charlie,
Here's,
we can't see a presentation if you're showing one.
oh really?
No,
Okay.
just seeing your icon CV.
Okay, let me see what's going on here. I'll try this again. Okay, it now says I'm screen sharing, and then I'm going to start again from the first slide. How's that?
Still not seeing it.
I can see it, Charlie.
Oh, that's it. Okay, we got it. Good.
All right. All right. So we'll move on to the second chart, which is the standard operational amplifier. And I chose the LM358 when I did the earlier presentation simply because I happen to have the data sheet for it handy and have a few of them on the bench. So I thought it would be a good place to start. So it took a kind of a standard circuit with a gain of 10, and that's with like a 5K feedback resistor and a 500 ohm series resistor. This is the inverting format. And if we put 1 volt peak to peak into it, we get 10 volts peak to peak out. And most of us would go, oh, okay, 10 volts peak to peak. We can power this with 12 volts, and we'll just use a voltage divider for the mid-rail reference, right? That should be just perfectly fine.
We're still looking at the first slide for some reason.
What are you seeing?
Einstein and Darwin.
Going to change?
Not yet.
Oh, I thought it was me. I just logged
Oh, there it is. Okay, got it.
Got it now?
Yep, we do. I do.
Okay. All right. So now that you've got this slide, it's time for me to move on to the next one. And so the way we would do this then is we would take, our standard between 12 volts and ground, and we would put a couple of resistors of the same value, 1K or 10K or whatever we choose to use, to create a rail in the middle here that's about halfway between our 12 volts and our 0 volts, and filter it. If we're going down to lower frequencies, some nice big electrolytic caps like 220 microfarads, and usually something like a 0.1 mic on there as well. And if this was an RF amplifier, we probably would just use 1Ks or 10Ks and the 0.1s. We wouldn't even bother with these 220s in here. So this looks like it should work. We've got 1 volt peak to peak coming in, so we've got 10 volts peak to peak coming out with that gain of 10 here with a 5K over 500 ohms, and we've got a 12 volt rail, so everything should be just fine. Except when we go off and look at the data sheet, the data sheet tells us that with a 1 milliamp of current flow, which we will have with a 5K ohms to this virtual ground here and a maximum upper peak of 5 volts, basically. 5 volts, 5K is a milliamp. So we'll have a milliamp of current flowing, which says that in the worst case, we can only swing that voltage to within 1.4 volts of the upper rail. So if we try to go, any closer than 1.48 volts, it's not guaranteed to work. We'll be clipping at the top. Similarly, on the negative rail, with our milliamp output, we can only get, worst case, within 1 volt of that lower rail. So if I add that 1 volt to the -5, that says need to be able to go down to, we'll need a -6 volt on the negative side as the absolute minimum. And on the positive side, our 5 volts that we need to swing plus another 1.48 means that we need, 6 plus 6.48, we need 12.48 volts in order to pass that 10 volt peak to peak signal without distortion. So our 12 volt supply is simply not going to work unless we're willing to accept a bunch of distortion on our signal, which we certainly shouldn't. And if you're wondering why we can't actually swing to the rails, it's the positive VCC rail, this where the output is, you've got at least 2 diode drops here from these 2 transistors. So that is 1.4 volts, and then there'll be a bit because of the current regulator here, and a bit because of this resistor that's here. And at the end of the day, 1.48 volts is what you can do on that side. And on the other side, you've got a PNP here. So again, 0.7 volts. Plus about 0.2 over here gets us to, within getting pretty close to that volt that they talk about in the spec sheet. So it's, when you look at the actual circuit inside the chip, it's pretty obvious why we can't swing right to the rails. So let's talk about noise now that we have talked about the DC bias problem and whether or not we can swing close to the rails. First, a definition of noise in this kind of circuit is, and what noise is, it's an unwanted signal with respect to a reference point. And this is absolutely critical, that it's with respect to a reference point. If we, come back to our circuit here, for instance, if I've got a volt of noise on the 12 volt rail, and a volt of identical noise on the 0 volt rail or the ground rail, then the whole everything with respect to that ground rail, it's all going up and down the same amount, and therefore we don't see that noise because the exact same unwanted signal, if you like, exists on both of the rails. Making sure that you're using the right references is critical if you want to know what your signal looks like, and what kind of a noise we're actually having in the overall op amp. Having more than one reference point, and almost all of us have done this. We go to look at something with the scope, and we clip on to any kind of ground point that's handy. We're probably going to see an invalid measurement, or at least one that's questionable. But these multiple reference points that we're using are things like ground loops. Um, they're responsible for almost all of our noise problems, whether it be ground loops or common mode noise that's coming in that creates, the RF in the shack, um, uh, electromagnetic interference with our computers in the shack. All of these things really stem from having multiple reference points. If your computer has a different ground point than your radio, there will be some potential between the two, and usually that manifests itself as noise, or even nastier things like resetting your computer, or other issues. So, I mean, we're talking about op amps here, and we're going to focus on that. But noise needs to be a system-wide consideration. You have to be very careful and think about it all the time. Do you have multiple reference points? And to be honest, in a system, you probably will need to. But do you have a noise relationship between these or not? What is the relationship of them to each other? Very important. Like our buddy Einstein said, everything is relative here to whatever the reference point is that you've chosen to use. So here's our two sort of favorite amplifier configurations. I see um, most of the folks in SOAREX like to use this one, the non-inverting amplifier, where we inject a signal on the positive input, and we use R2 over R1 plus 1 is the gain for it, times whatever this voltage is will give us the output voltage. And then there's the one that I tend to use all the time because I'm lazy at math. If we use the inverting input, the gain of the stage is just R2 over R1. There's no extra 1 plus in there. So it's it's easier for me to keep straight in my head what the gain of the stage is, particularly, if the first stage has a gain of 10 and the second stage has a gain of 10, overall a gain of 100 is a little easier than if the first stage has a gain of 10 or 11, let's say, and the second stage has a gain of 11. Now we've got a gain of 121. It's just simpler for me, so I like to use the inverting input. But in any case, the output is um, these 2 points. The difference between these 2 points is what drives the output. So the voltage on the output, if you like, will do whatever it needs to do to cancel out this signal. If this is sitting at the reference point, so if this is 1 volt coming in here across 10K, I will need to put 1 volt in the opposite direction across this 10K so that this virtual ground node here has 0 volts on it. But it's worth noting that, with respect to this ground point, any unwanted signal coming in here, or in fact coming in through this ground point, is going to manifest itself as noise. Same with the other circuit. Even if you're, driving your main signal in the positive input, and the negative input is a reference, if there's noise, particularly at this node, it's going to manifest itself as noise on the output. So in short terms, the 2 places noise can get in are the negative input and the positive input. Also, there's a potential for noise to come in through the power rails. And we'll talk about that a little bit, and why that's not quite so worrisome in a minute here. I'm just going to bring up the other op-amp configuration, the differential amplifier, where you've got two signals coming in. This one kind of shows the noise problem better. So if we, pretend that either V1 or V2 is our noise source, it's going to get added either in a positive fashion or a negative fashion into the amplifier, and hence appear in the output multiplied by the gain of the stage. This is kind of important to look at, because when we go to our standard situation here, where we bias our negative input, we've got our 12 volt on the positive, we've got ground on the negative, and then our reference is this voltage divider here between the two 1Ks and some filtering. If there's a lot of noise on the 12 volts, well, half of that noise is going to appear here. And maybe it will get shorted by these caps down to 0 volts, but some of it, in all likelihood, is going to go through, depending on just how great a job you've done at filtering here. And of course, so that noise off the supply is going to end up getting into this positive input, and consequently, it will be at the output, amplified by the gain of the stage, which, in this case is a factor of 10, right? Of course, that power supply noise is also on the op-amp pins. So, can it in fact get into the circuit through the power pins? Well, once again, let's go look at the spec sheet. Bit of a broken record, go look at the spec sheet, but you can see here that for our 358 amplifier, the one in the middle, the power supply rejection ratio is typically 100 dB.
Sorry, Charlie, you didn't advance the slide.
Well, it's advanced on my screen. What are you seeing on your screen right now?
See the similarity to previous slide, and then it's got that op amp with the voltage divider.
Okay, you're seeing that. I don't know what's going on with the presentation tonight. It's advancing quite happily on my screen. Are you seeing it now, the spec sheet?
No.
Hey Charlie, I noticed I keep getting like a bandwidth, something, it pops up saying blocking video to conserve bandwidth. I don't have a bandwidth problem. So yeah, I don't know if you've got your performance settings set too low.
You think I should set them higher?
Yeah.
Okay,
I'm getting the same message.
Okay, let me see what I can do here. I'll just pop out of the presentation for a second, and I'll see if I can.
On a side note, I was getting this message for the first time like every 15, 20 seconds 2 weeks ago.
Yeah.
Okay, so I have stopped sharing. Okay, I'm going to pop this up.
Eric, it could be a Jitsi thing, the Jitsi server.
Yeah. True.
Okay.
Do you have your performance settings tuned down, Charlie?
I dropped them back a notch, yes. So I've cranked them up full.
Yeah.
And I'll see if we'll try sharing again here. All right, now let's go back to the presentation. It's it's kind of important to see the slides on this one, because it's a huge part of the discussion, right?
Okay, there you go.
Seeing the spec sheet now?
Yep.
Okay. So for the as I was saying, for the LM358, if we look at the power supply rejection ratio, it's 100 dB typically, and in the worst case, 65. Also, if the noise is on both the positive and negative pins, that's a common mode signal, and a common mode rejection ratio is like 85 dB. So um, if we're going to get noise into this circuit, it's really got to be on one of the pins, not necessarily on the other one of the pins. And it's not coming in through the power rails. The power rails are going to reject that quite nicely for us. And if we look at the circuit again, you can kind of see why the power supply rejection is so nice. They're using constant current generators to feed the transistors inside. And because these are constant regulators, it will ensure that the same current is passing through here regardless of what voltage is on top. And if that voltage bops around in terms of noise, it doesn't matter. The current regulator will take care of that. So and on the negative rail, same kind of thing. There's another current regulator coming into the drivers for the output. So those
Sorry,
are
the slide didn't advance if you're showing the circuit.
I don't know what to say, guys. Let's see if I can try it one more time. Still no new slide. Let me try.
Okay, that's the one with the
That's
current regulators, right?
Yeah.
Yeah.
That's what I was just talking about with the current regulators. Okay, I'm going to try a trick here when it comes to advancing the slides. I'm going to try dropping the existing slide, advance to the next one, and then share it again. So you can see this one. We don't have dual power supplies, but we can fake it, right?
Yeah.
Yeah. So this is our commonly used circuit up here, and this is another chart from the January discussion about this circuit. While we think it's providing a nice balanced mid rail, in fact, when you look at the resistor tolerances, we get moved off from the center by a bit. Just as we just simply sit down and do the math. The voltage at this common node is R2 over R1 plus R2, and if it's a 5% resistor or even a 1% resistor, it's not going to work out to be, if we've got a 10 volt supply, it might be 5.2 or 4.8, for instance. So that again impacts how close we can swing to the rails, and so we need an even bigger voltage for our 10 volt peak to peak signal we were talking about earlier. But if we look at the decoupling caps, we can sit down and calculate, well, what's the cutoff frequency for this? I mean, this is a filter. The objective of it is to filter out any noise that's on the rail. If I do the calculation with these capacitors and resistors, I will get 0.724 hertz. And as a rule of thumb, if we multiply that calculation by a factor of 10, let's say, then this virtual ground that we've created here is going to be good down to 7.24 hertz, or call it 7 hertz. Which isn't too bad for an audio amp. That's pretty reasonable. We might have some very low frequency noise, but nothing too terrible. But if I look at what we typically do in our circuits when we do it, and I'm as guilty of this as anyone else, I'll slap 0.1s on here, or maybe even 1 mics on here, and don't bother with these big electrolytics. And if I do that, now suddenly the cutoff frequency is 1592 hertz or 1.5K. And then you multiply that by 10, and suddenly the ground is only good down to 15 kilohertz. And if we're using 10K resistors, which we often do instead of the 1Ks that are here, well, lo and behold, this is only a ground down to 150 kilohertz. Anything below that, and it's not ground at all. So the noise that's on this rail is going to get fed, directly into that circuit. I'm going to try one more time here to see if I can advance the slide.
Yeah.
That did advance. Okay, good.
Yeah.
So I've put a couple of stages here, to talk about where the references are and what certain voltages would be around, right? So if we've got our, 12 volt and 0 volt, then with our mid rail that we used on the previous slide, our output is going to have a DC bias of 6 volts. And our input signal is going to have a DC bias probably of 0 volts. Like in a lot of our circuits, this is a transformer winding to ground. So 0 volts DC here, 6 volts DC out here. We need to AC couple this in here. So we got to put a nice big cap in here. This stage, again, 12 volts and 0 volts, where we've got a 6 volt DC output. Then if we're using the same voltage divider for reference, no worries. We can put a wire between these two and life's good. If we're using different voltage divider references, because of that difference in tolerance of the resistors, we could be off by 0.2, 0.4 volts here, compared to the no signal condition over here, and 0.4 volts multiplied by our gain of 10 here, is 4 volts error out over here. So we'll be screwed up. So we need to AC couple between these stages as well. Put a nice big cap in here. These nodes are drawn differently than the ground symbol, really to depict that they are not the same thing. So if I come along with my scope, and I hang it on this reference, no problem. I've got a good ground on here, and I go probing around in the circuit. If I clip it over here, I'm putting the DC connection of the scope to what's effectively 6 volts DC. Now, maybe that's okay with the scope you have. Maybe it's not okay with the scope you have, and you could, potentially damage the scope, or in the worst case, or even in the best case, you're going to screw up the measurement, because the signal is with respect to what's here, and that includes whatever weird noise is on here. As long as it's relative, that same weird noise is everywhere else. It doesn't impact your circuit. You'll never hear it. You won't even see it on the screen if you poke your scope here, to put the ground connection here. However, if you clip it over here, for instance, and you're careful to AC couple that point, the noise that we see here, this noise is in fact going to find its way through and get amplified through and end up appearing on our output. And again, when we use this circuit, did we get a change on slides this time?
Yeah.
Okay. Our noise that's coming off the 12 volt rail over here with our single-ended power supply is going right into this point, and consequently this, with respect to that signal ground that I showed on the previous slide, is going to get amplified, multiplied by 10, and multiplied by 11 in this case, because it's coming in the positive input, and that power supply noise is going to be, going to be coming into the output and coming out your speaker or headset or whatever you need that clean signal to be. So slide change again.
Yeah.
Okay, so if we have a single reference point, as long as the connections are relatively short. So I didn't bother to change the symbol on here, but these three things are exactly the same ground. You achieve that by using a differential supplies, so that the middle is the reference throughout the circuit, ground is the reference throughout the circuit. It could be plus minus 5, it could be plus minus 10 or plus minus 15. It could even be, depending on how far you need to swing that voltage, once your final output voltage, you could have like a 10 volt on the top and a minus 5 on the bottom. That will all still work. Only you'll only be able to swing negatively, with respect to the minus 5. You could swing further on the positive side, but that wouldn't be a sinusoidal signal going through. Because our signal is referenced around 0 volts DC, well, the output's going to be at 0 volts DC, and the output on the next stage is going to be at 0 volts DC. So you can physically connect all these things with just a piece of wire. You don't need capacitors in there. You don't need any resistor dividers. It's all taken care of. And in terms of the noise reference, you can clip your scope on any of these points, the ground pin on your scope, probe to your heart's content, and you will always see the same signal, amplified or unamplified, et cetera, but the same noise component will be everywhere in the circuit. And consequently, it will, in all likelihood, be canceled out because it's with respect to these grounds. And that's, to be fair, that's as long as the connections are short. If you start stringing 3-4 feet of wire between these points, you're putting up an antenna farm, all bets are off. And also, to be fair, long pieces of wire have inherent inductance and resistance, and so when you do that, these points are no longer the same. But for the sort of frequencies that we play with, keeping these things down to on the order of inches rather than feet, you'll be fine. You'll have much cleaner signal. Now, doing that again, it is harder than you think, right? As I mentioned, there's resistance, inductance, and even capacitance to other signals, even if these are connected with a track on the backplane or a large backplane. When we're laying up boards, it's really important to keep connections between these points as short and direct as possible, and fat and thick, because you want them as much as possible to be the same, because as our buddy Einstein says, everything is relative to this point. And also, choose your test instrument's ground location carefully. Make it as short as possible. Choose as close to one of these points as you possibly can, not run a track over to the far corner of the board to a pin where you can hook your ground on. That's making your measurement instrument probably see way more noise than it should. And whatever point you connect that ground to, that becomes the reference for all of your measurements. So final conclusions: if you have dual power supplies available and can use them, do so. It makes life so much easier, makes the noise problem so much simpler. Just do it. If you have to create a mid-rail reference, and let's face it, there's lots of times you only have a 12 volt supply for a battery or something, create that mid-rail reference only once and then use it everywhere, because it's now your only reference. And when you're hooking up measuring circuits and whatnot, be aware of the DC bias that's going to be on there. But decouple the heck out of it. Make sure that there's a very low impedance path to ground for noise signals that are coming in on the power supply, because this is a great way to bring noise into your circuit. Again, conclusion, reference point is critical. If your instrument doesn't have the same reference as the signal source and the signal sink, your measurement's really meaningless. You'll be, try disconnecting the ground and see what your scope looks like. It's that kind of a problem that you just got so much noise that's overriding the signal that you're trying to look at. And if at all possible, try for a single reference point, and be aware of any compromises you make. And you can't do it perfectly. We all get that, but be aware of it and think about it, and kind of run it through the old brain before you commit to ordering a board. And finally, read the data sheet. It's got lots of good information in it, but for all of these things, we spend a huge amount of time, for instance, in these op-amp circuits with, trying to decouple the power supply to the op-amp. We put caps across the power rails on the op-amp itself. We'll stick an inductor in series with it. We'll do all kinds of crap. But the op-amp itself has 100 dB of power supply rejection. So is that really where to be spending our decoupling stuff? Maybe put a bit more of it on the real places where noise is getting in, around the inputs, around the voltage references, and so on. Yeah, I think that's all I have to say.
I can't see who is.
I'm just gonna stop.
It's Dave. Go ahead, Dave.
Yeah, Charlie, very good. I have one question. The slide, well, not the slide, you were talking about, using dual rails, which, it's, I guess that's the best thing to go and do. Now, I just wanted to pick your brains to see whether, I know that Kevin, I don't know if Kevin is on the call yet. I know Kevin has been using charge pumps with the power supply he's building, or using a buck converter to generate a negative. I don't know if it's a charge converter or a charge pump or a buck converter. I don't know, whatever it's called. Anyway, I just wanted to know noise, because if you're using some kind of charge pump or a buck, it typically has a frequency of hundreds of kilohertz or hundreds of kilohertz, which could bleed into the circuit as noise. And I just wanted to get your sense for whether that's something we should be careful of, and if so, how can we remove that?
So that the problem is not the charge pump per se, it's the charge storage. So as long as it's not the noise that's on there isn't effectively taking the rail below where it needs to be in order to handle the signal, and itsy bitsy teeny tiny slices, it shouldn't be a problem. A big cap on that output should be just fine. I think what's probably more of a concern for us in something like the backplane radio is that the input to those devices is going to create a lot of current pulsing noise on whatever master supply is coming in. So let's say we're running 20 volts to power the whole board. There's a good chance that we'll be creating RF noise on the line that's going back to that supply. And so it may make sense in that case on the input to those switching supplies to put a millihenry inductor and 47 mic cap or something like that to keep that noise from getting back into the absolute supply. But I think on the internally, if we just put a big cap there, we're probably okay.
Now, when you say a big cap, are you talking about like electrolytic or just a ceramic, a large value ceramic cap? Because I know like the electrolytics have a smaller internal resistance, so it'll short stuff quicker to ground.
The electrolytics actually have a higher internal resistance. So that's the problem, and inductance typically in the leads for them. Generally, we bypass an electrolytic with something like a ceramic for the higher frequencies, much higher frequencies.
So then you'd use both, like, because in your one slide, you had a large honker of a capacitor and a smaller one, like a 0.1 microfarad. So you'd use a electrolytic plus a smaller capacitor, and I guess the smaller capacitor acts as a shunt to take the noise to ground.
That's right. So when the large electrolytic at lower frequencies, it's like a battery. It holds its charge lovely, no issues at all. As the frequencies go up, the equivalent series resistance and the equivalent series inductance in that device start to dominate, and pretty soon, if you're up in the tens of megahertz, for instance, you're suddenly those parasitic variables are dominant. They're the impedance curve gets lower and lower and lower and lower, and then it starts to rise again as the frequency goes up. And so when you get up into those higher frequencies, that's where the 0.1s kind of come into play. I mean, the other thing you can do too, and you have to analyze the circuit to know for sure whether it's sufficient or not, but you could get away with perhaps just a large ceramic, like a 10 mic ceramic, or you can get even a 47 mic ceramic these days.
Yeah, because that's what typically I would do, is I'd use a 10 micro, what's a 1206?
Sure.
And a 0.1. That's what typically I do, right? But
yep.
Here's a question though about using electrolytics. You said that they're like a battery, which makes sense. They store energy. That's what they're for. Now, in most of the radios that we build, we'll typically have a TX power and a RX power. Yes. Now, if you turn off the TX power, it means you've got quite a bit of energy, or you could have quite a bit of energy in those capacitors that has to bleed out into the TX circuit. Couldn't that cause problems as well if you put too big of a capacitor?
It's the charge time that becomes an issue with too big a capacitor. The fact that there's a charge sitting there, you don't really care when you turn it off. Who cares if it's sitting there? It's like, the old CRT televisions. You could leave them unplugged for 2 weeks and stick your finger in the back and get thrown on your butt on the floor. It hurts nothing for the charge to remain there. It will bleed off eventually, but
in theory, you've got like some sort of transmit circuit, and I'm just thinking out loud, and it could be like an amplifier, or it could be an oscillator, or it could be something that now keeps running and could be generating noise when you switch over to receive.
Oh, I see what you're saying. Without a very specific circuit, it's kind of hard to say, right, Dave? But I mean, you can certainly, if you're switching off the transmitter or oscillator or whatever, choose your switch off point that the capacitor is outside of that switching point.
Yeah, I'm just kind of thinking, I'm just kind of brainstorming now, and that's because when I build these things, that's some of the things I think about, because with the Phoenix, when we built that, or the first Phoenix revision, we built that, we had very large caps, and when you keyed or you let go of the mic, you would hear a chirp, you'd hear some jitter, some crap, right? And it's also, and I figured it's got to do with the capacitors, right?
Perhaps it does. I'm not sure where you were turning it on and off without the schematic. But if the capacitor was inside that loop, yeah, it would have to bleed down, and that would cause a chirp. Probably even more likely, it was the oscillator circuit, because the oscillators don't switch on at the perfect frequency and then switch off immediately. They kind of frequency ramps up a bit and ramps down a bit, right? And that's what causes the chirps in CW typically.
Okay, I'll monopolize your time too much. I'll give someone else.
One of these days we'll sit down with a whiteboard and a couple of beers and solve world hunger.
Okay, very good, Charlie. Anybody else? Questions for Charlie?
I have a comment, Michael.
Yes.
Go ahead.
We have, well, I'm in the process of actually building the backplane audio amplifier, and it's got a dual NE5532 op amp. And as far as the filtering is concerned, I've got 100 microfarad cap, and also 100 nanofat at 0.1 in parallel right across the power supply. So I guess that's okay. I don't really know, but I guess it is. The other thing we were going to do, when I first designed the circuit, I was going to supply each half of the op amp with its own bias resistor, like 2 sets of bias resistors. And what we've now done is just gone to 1. And I'm not sure whether that's a good thing or not. I guess from what you're saying, it's probably not a bad idea.
Yeah, that's a great idea. 2 sets of bias resistors is not a good idea.
And, just lucky, I guess.
And the filtering that's across the amplifier, I can't see it hurting anything. It probably is. When you get the boards, you could leave those off and see what happens, just for giggles, when you do the first one, to do some bench measurements. But I'm pretty sure you won't see a whole lot of difference with those caps in place or gone. The smaller one probably isn't a bad idea to keep anyway, but I don't think the bigger one's doing much for you.
Well, I've already built the board, at least as far as that's part of it's concerned. So I'm just going to leave it the way it is. And the other thought is the dual supply, which with the backplane radio, I guess I could do, because there's plus and minus 12 volts on there.
Yep. And
so if I really wanted to do another incarnation of this, I could do plus and minus 12 volts, I guess.
Yeah. And well, have a look and see how noisy it is. This is probably far more important in the RF sections. Because the impact of noise is so much higher when you in the RF sections. You're dealing with teeny tiny signals and so on. By the time we're down to audio, it's the noise is going to be small enough that it's probably not annoying anyone at all, and it's probably even at frequencies that isn't being amplified because of the way the amplifiers are laid out on the board. So I wouldn't worry about it too much. That part of the fun of what we're doing is we build it up and we see what works and what doesn't work and try different things, right? So,
well, it's interesting. Also, the 15 kilohertz you talked about, the low cutoff, and that's quite high in terms of audio signals, isn't it? So I don't know. We'll see. But hopefully,
it absolutely is. But you can calculate that, right?
Yeah.
With the components that you've chosen, and just see where it's going to be, right? It's a pretty simple formula.
Okay, very interesting and relevant right now, because I'm trying to get the circuit to work. Yeah, okay, thanks.
Very good. Anybody else? Question or a comment? Okay, we're good. Okay, thank you, Charlie. That was interesting. Like I said before, I'd like to see your DC bias presentation when it's available.
Well, I think the recording is there. It was January 7th or something like that I did.
Oh, yeah, that's right. Okay. Actually, I don't know if I put that up on YouTube or not. I have to check. Okay, very good. Thank you, Charlie. Kevin is here. Finally. You want to go ahead with your cool chip?
Sure. Hi, guys. How's it going? Let's see. Share, and I want, which window? I want that window. All right, should be able to see that.
Yes, sir.
Okay, so anyway, so this month I found this MM5130, and it's an RF switch. And you go, well, why are we talking about RF switches? We have lots of RF switches, right? We have pin diodes, we have FATs, we have relays, but they all have their, they all have their thing. That may be good or may not be good, depending what you want to do. Anyway, so this company, and it caught my eye because it was, I don't know, they were announcing some contract with the U.S. military or something for this stuff. And I think it has to do with like a lot of radar stuff. Anyway, so this is an RF switch, but it's based on MEMS technology, which is like, how they when they engrave the chips or create the chips, instead of creating transistors and FETs and whatever, gates and wires and stuff, they actually create mechanical devices. So they can have gears and levers and membranes, motors. Somebody created a motor on a chip. And then these mechanical things can interface to the real world. So when you get a pressure sensor, it's got a little lever in there that senses the outside pressure. And then that lever capacitively couples to something else in the system. And from that, you can run an oscillator, and from the frequency, you can determine the pressure. So this is sort of a variation on that. But it's a little different than what I've seen before. Anyway, so this is some of the capabilities. It switches one signal to 4 RF outputs, so single pole 4 throw. DC to 26 gigahertz, 25 watts. That's at 6 gigahertz. It actually goes higher when you get down a little bit lower. 0.3 dB insertion loss at 6 gigahertz, 25 dB isolation, rated for 3 billion operations. So that goes way beyond any relay I've ever heard of. And turn on times in the microseconds. The gate bias current, 2 nanoamps, but it's 89 volts typical. Not exactly your normal bias voltage. You can't hot switch this. And just by the voltage there, that tells you that the actuators actually use electrostatic forces. And when I'm done here, I'll put there's a YouTube video that kind of shows how this thing works a little bit better than what I'm going to do here. But so this is the block diagram. It's very simple, just RF in, and you've got one of 4 RF outputs that you select by enabling one of the gates. That's it. Nothing fancy. How it works is it makes these tiny little actuators. So there's like an actuator, this silver thing moves up and down, and then it touches the pads and makes the connection. And what they do is they take a bunch of them, put them in parallel, and then actually put another set in series. So that becomes one of the switches, from what I can gather. And also that increases the power capacity and the voltage capacity. These things will withstand apparently 150 volts across this open. You obviously don't want to switch that, on with that kind of power level there. Or at least 150 volts before it destroys the chip. And then what they do is they take all of those things in there and then they encase them in glass, and they have these electrodes coming down to short or to touch the various pads there. And there's a controlled atmosphere in there because obviously you don't want these things switching with like oxygen and things like that in there. So they put some kind of atmosphere in there. So there's a lot of technology in this chip. Here's some charts, just return loss. So it's not too bad, even all up to 20 gigahertz. I think minus 17 is like 1.5 to 1 or something, 2 to 1. I forget what the return loss things are, but I mean, it's not that bad considering what you're doing here. Power handling capability. So if you're getting down like where we are, you're talking 50 watts for this thing. So, And that's what these things for. Like it's for antennas with rapid switching, right? Beamforming, phased array antennas for the military, tunable filter banks, antenna tuning, switch matrices. Look at the size on this thing. Whoops! Oh crap! 2.5 millimeters square. Again, like last month's chip, it was like, I think that one was also like 2 or 2.5 millimeters square. I can't imagine soldering this thing, but anyway. But I don't think we're going to use too many because they're $177 each at DigiKey. So anyway, or the evaluation board is 10 times that if you want to play around with it. So anyway, that's it.
That was cool. I think I'm going to order one. Yeah, sure. It's pretty cool.
It's. Oh, there's Dave.
Yeah, go ahead.
Dave.
Yeah, Kevin, it was it's that's a really cool chip. It is those RF switches. I just came across a chip that I'm using. It is a switch, but it's meant for power, switching power on and off, as opposed to having a like a MOSFET or not an N gate, a P gate or whatever it's called, MOSFET to switch your power on. This is a discrete chip and it senses the load. So if there's nothing connected to it, it's got a pin that tells you, hey, nothing's connected, or you've got something connected, right? And it allows you to switch like amps on. It's a little tiny chip, and it'll run amps through the output once you switch it on. So it's kind of a cool. It's like a switch, because I saw that chip. It said DC, and I thought, oh, you could switch DC through that. I'm sure you can't switch a lot of amperage through that.
No. And actually below 5 megahertz, they actually derate it from that 50 watts. It drops down significantly.
Yeah.
So, but from 5 to like gigahertz, it's good for like 50 watts.
Yeah, because I use this chip in my rocket altimeters, and I can switch. I could fire a charge, which typically takes like hundreds of milliamps, but I can fire a charge up to 1 amp, which is like an engine start charge. Mm-hmm. So it's pretty cool. Anyway, it just kind of reminded me of that chip I'm using.
Yeah, it's I came across it. It's like, wow, that's kind of neat. I wonder how much they are. And I was like, I was like Ken. I was like, oh, I'm gonna go buy one. No, I'm not.
Okay. Anybody else?
I just wanted to say that this technology is really cool. The MEMS technology, I've followed it for quite a few years. We all have some of it, like the seatbelt or the airbag actuators in our vehicles are all MEMS technology, right? And,
yeah, even in your phone.
Yeah, and
the barometric pressure sensor in your phone, it's MEMS technology.
The coolest use for the technology I saw was some guys who were working in high-speed optical fiber optic transmission were using MEMS devices with little mirrors that would pop up to switch the beam of laser light down out a different fiber, depending on the destination of the signal.
Oh, those big laser projectors, they're all MEMS technology. There's little mirrors that just flip back and forth.
It's amazing stuff.
It is. It really is. And I can't wait to see what they're. Well, I have another chip for next. I was looking at another sort of not chip, but an assembly for next month that kind of boggled my mind. But or I can talk about it now if nobody has anything else.
Very cool. Anybody else? Okay, Kevin, that was I'm gonna order one tonight after the meeting. I won't be able to retire then. Okay, thanks, Kevin. Who's up next? Oh, Eric, you want to talk about FDIMn North?
Sure. Yeah, a little update. By the way, don't bother ordering. I've got 5 of them, so if anybody wants to borrow one or use one for a while, just let me know and I'll bring it to FDIMn North, and so it's all good. All right.
At the e-store.
So, where was I here? Okay, let me screen share. But before we continue, was just curious, was everybody getting these bandwidth or video turned off to conserve bandwidth messages?
Yeah, I was getting that.
Yeah, in here.
Everybody.
Yeah,
Okay.
me too. Yeah.
Yeah. All right. So something that I just came across that we might want to give it a shot, because it seems turning everybody's video off, which was a potential suggestion, didn't do much. And it seems to only happen during the presentations. You know, it's weird because like it doesn't turn it off with a video feed where it's like moving around, but with a static page, it seems to want to conserve bandwidth. I don't know. I don't quite understand how a static, page will kill bandwidth. But I just put in the chat there. There is a beta channel for Jitsi Meet, which might be a improvement as far as slightly more advanced features that they have. That's a possibility. So anyway, we could consider trying that for our next meeting, just to give it a try and see if it makes a difference with our presentation bandwidth issues. So it seems to be a problem as of late. I don't know if maybe Jitsi Meet is being oversubscribed or what. Bandwidth on their service is being divided too finely, but plan B could be starting to investigate hosting it on a cloud server of our own of some sort. That would involve a cost of probably nominal amount, but that's a potential as well, so that we don't have to be constrained by whatever Jitsi is having available for free to everybody and anybody that wants to use it. So anyway, sorry, Dave, you wanted to make a comment?
Yeah, at the risk of having stuff thrown at me, this seems like SOAREX seems to be stable. It seems to be working well. People enjoy it. So why don't we spend the money and get Zoom? Pay for something, have everyone chip in a little bit of money, a few dollars a month, or whatever it is, and just get Zoom and pay for it, because this seems to be beneficial to everyone. So I would suggest we do that, because Jitsi, it's free, and these are the kind of issues you get with free, right?
Disagree, Dave. I do multiple Zoom meetings in a week, and it's worse than Jitsi.
Really?
Well, then not Zoom. Get something else. Whatever. I'm not saying get Zoom. I'm just saying we get a paid subscription, something to
The video's off.
we could go use.
Okay, you're sure?
Yes, I'm sure.
Yeah. Okay, that's good, interesting feedback, Joe. I would assume Zoom, especially a paid instance of it, would be almost flawless, but not so, eh?
Not so.
Huh. Okay. All right. Well, like I said, maybe again, I think chipping into a getting a whatever cloud-based server space somewhere, and then doing our own, having our own little Jitsi, and then we can do whatever we want. We can have a little file zone and everything else, right? And I think they're cheap, $5-10 a month or something. I mean, hell.
The problem is.
That's a good.
The problem is, Eric, with how do I? Oh, my hand's lowered. The problem is with that, Eric. In theory, that's great. Yeah, we could go get a cloud server, put it on. Who's going to manage that? Okay, who's going to pay for? Because a cloud server, it's the free tier is for a limited amount of CPU cycles, limited amount of disk storage, limited amount of bandwidth. As soon as you exceed that, and Jitsi will exceed that, you'll have to pay for that hosting now. So
yeah. You know, I'm thinking like $10 a month or something for like a basic level or whatever. So it's not just a free service,
I
and
think
maybe
$10 each per month.
you think I don't know.
Do you think you're going to get like a Amazon for like $10 a month?
I don't know. I don't. I have no idea what the thing is, but you know, then I could approach the VE3OI Foundation, and maybe they would sponsor it, perhaps. But anyway, okay. Well, yeah, it's a good point. So we've got to see what's out there and what the options are. So, Charlie, yeah.
Yeah, just one thing worth noting is the quality settings are counterintuitive. Like I turned my quality settings down so that I would not be bandwidth constrained. Lower quality should consume less bandwidth. But in fact, the opposite is true. If I turn it up to higher quality, then the problems went away.
I had the same issues.
Yeah. Yeah, and I like when I was looking at your connection quality, Charlie, when you were doing your presentation, it kept going to you know, sort of an inactive state. I don't know, it's kind of weird, but you have otherwise no internet connectivity issues, right? Where you are? Generally?
Not that I'm aware of. Yep.
Yeah. Yeah, so I don't know. I think it's the connection to Jitsy's servers that's probably more likely the issue than our individual pipes to the internet. Michael?
For what it's worth, the Mississauga Club, we use Zoom, and it's paid for. It's about $200 a year. That's what it costs us, for whatever that's worth.
Okay, and quality?
Pretty good as far as I can see. Like I haven't had any problems doing presentations via the Zoom or watching them. They seem to be fine. So I don't know. For whatever that's worth.
Yeah. Okay. Good feedback as well. All right. Well, let me try screen sharing myself here and see how that goes. I think I should be able to do this. So, unfortunately, our reservation at the Georgina/Keswick location was without explanation canceled on us less than a week or two ago, very recently. So that was just like I said, no explanation. These things do happen sometimes with Airbnb. There's no guarantees. Not the first time it's happened to me personally, but first time for a SOAREX event. Anyway, so I got on the task to find an alternate suitable location, and came across a spot that looks just fine. It's north of Coburg, maybe, I don't know, 30 minutes or so, 30-minute drive north of Coburg. It's on the south shore of Rice Lake. So it is a new build house in a little town called Roseneath. So anyway, there's a bit of an outdoor area, which bodes well for any kind of outside antenna setups. There's, a tree there. Again, I'm not sure exactly what this is a picture of. Particularly, I don't believe that's the house that we're looking at. But anyway, the house itself looks fairly reasonable. It is, I believe, 6 separate beds, plus a sofa bed or what have you in the living room. So I think comfortably sleeps up to 6 or 7, each in their own beds. So anyway, so I have gone ahead and booked this particular place. It has a central living room area with a television on the wall. I think that might have been in one of the earlier pictures, but anyway, this place has the advantage, well, pros and cons. Disadvantages, it's a new build, so it is a unsodded, ungrassed, unlandscaped exterior. So seeing as it's May, it's hard to say with the weather, but we may be looking at a muddy area outside. Not that we're going to be spending a whole lot of time outside, other than perhaps setting up equipment, antennas, etc. But anyway, the host did send me a message in advance indicating that she hoped that wasn't a problem, and I indicated no. The advantage of the place is considerably less expensive than the place in Keswick, Georgina, that we were looking at, probably about 40% less, which is nice. So that means that the cost per person goes down commensurately. So depending on how many people are staying any given of the 4 nights, the price per person per night is anywhere from like $33 to $44 or so, based on the $264 per night cost for the whole house. So pretty reasonable, I think. It's hard pressed to get a hotel room these days in major areas for that kind of rate. So we got a whole house that holds plenty of people. So anyway, that is that. So we are on for May the 13th to 17th. And that really is all of the updates I have to share with you for now. Ken, come in.
Yeah, I did a street view of that picture of that house, and
Yeah,
it does not exist.
Empty. No, it doesn't. Yeah, because I think when I mentioned to you when the Google satellite passed over, it was in a field, basically. So it is a brand new baby, just born probably in the last 12 months or so. So yeah, makes sense. That what is it? As they say, username checks out. So
yeah. We're probably better off getting a GPS coordinates and just plop it into Google Maps.
Oh yeah, I mean, like there's actually a street address, as you can see on the screen share there. But anyway, so yeah, all systems go. We are about I guess it's 4 weeks today, right, for the event. So I will be posting I think like I did for the last cottage event, a spreadsheet kind of shared document that I'll post in groups.io, just so you can kind of let the group know when you're planning on arriving and departing, if you're staying over, and also if you're just planning on coming up for the day, to indicate that. So keep an eye out on the groups.io for that. I will also send out a formal overview of the location and all of that to those that are attending, and an invite to those that might be potentials for it. So anyway, that's pretty much the long and the short of it. I got to contact Rex again to see if he's going to be able to send up his actual FDIMn kits that he was going to be bringing to Dayton. If he could send some north of the border for us to, maybe participate remotely, and that's about it for now. So I'll pass it back to you, Ken, and stop the share.
I'm assuming this house is on a slab. It doesn't have a basement.
I would think it probably has a basement. That's pretty much code, isn't it, these days for a new build in Canada?
No. If you want a slab, your foundation's got to go down. On Ontario, it's 2 feet. Manitoba, it's 4. It all depends where you are.
Okay. All right. Well, yeah, no idea. That's not the kind of thing that's usually mentioned in a Airbnb listing, to be honest with you, that I've seen, unless they've got a finished basement that, is a party room or something like that. But being a new build, it'll be an unfinished basement of any sort. But anyway, well, whatever. not too relevant for us, is it?
Plus, if
Chris,
it
do you
did,
have plans for the basement?
no. I'm just wondering. Plus, if it did
Yeah.
have a basement, it would list it.
Yeah. Okay. So.
All right. Thanks, Eric.
Yep.
Okay, so we're I think we're done. Does anybody have any questions or inquiries? Go ahead, Dave.
Yeah, I went to AI and I put in a question about AI about Jitsi and bandwidth issues, and I posted the response in the chat, and it said one person's having bandwidth issues, and I think the person who's common to all this is, sorry, Eric, I got to throw you under the bus. You're recording, so I think maybe your recording has got the bandwidth issues, and that's why it's throttling back, because this was happening when you were slide sharing, when Charlie was slide sharing, when Kevin was slide sharing. So I think the only comment, if that AI post, if that AI response is correct, and it is in fact, something to do with a user having bandwidth issues, I think, Eric, it's probably your recording device that's having the issue.
Interesting. Well, yeah, because I've tried on multiple different systems, wired, wireless. The system that I've been using for years to record, without issue, is having that same symptom. So possibly. I mean, I'm not saying it's not, but I'm having no issues with my regular 20 to 25 megabit internet link. So to my ISP. I've checked that as well. So, I don't know. It's kind of a little mysterious. But
is it that recording PC? It's something that can handle this?
Oh yeah, absolutely. Well, like I said, I've done it on my existing that I've used for years, like i7s. It's kept up for years without an issue. And this is just the last, I don't know, 3-4 meetings, something like that. So I'm doing a speed test right now. I'm getting, well, not full speeds, but reasonable. Actually, it's kind of low on at the moment. So
I think the key thing is drop packets, not really speed. It's how many packets you miss, right? That gets dropped.
Yep.
I don't know. I haven't done networking for a long time, but I believe it's got something to do with that. But anyway, it's either Jitsi. There's a problem with what we're doing here, and it may be beneficial for us to look elsewhere. Anyway, enough said in that. Let's move on.
Yep. Okay.
Okay, so does anybody have anything else they want to bring up, or are we going to call it an evening? Well, I see no hands up, but there's no pictures. Anyways, gentlemen, okay, so our next meeting is, I believe it's May 6th. No, it's actually, May 6th, Wednesday, May 6th. And that's our mixer. And we'll see you guys then. Have a good evening.
Yeah, very good. Good
Thanks,
presentation. Thanks. Good night.
Thanks all. Good night.
Okay, ciao.
Thanks, everybody.
All right. Good night.
Thanks, guys.
Ciao.